Welcome to another Ultralight Airplane Design video from Ultralight Airplane Workshop. This is part 2C of a mini-series that we're doing on the structural design of the center main spar of the UWS-4 Ultralight airplane. In part 2A and part 2B, we worked on something called additional lift, distributed along the span of the airplane. In part 2A and part 2B, I talked quite a bit about how I use spreadsheets to do the calculations for the equations that we had. Well, here in part 2C, I'm actually going to show you some of that spreadsheet. I'm also going to give a really brief primer on spreadsheets themselves. And then we go into specifically what I did for the span-wise distributed load calculations, at least for additional lift. I should also mention there's going to be some follow-up parts on this mini-series, and there's at least going to be a part 2D. I don't know if there'll be a part 2E, but there probably will, because there's quite a bit to basic lift, which is what we're going to talk about in part D. So let's get started talking about a kind of a simple, quick introduction to spreadsheets, and then we'll jump into the calculations. So, a quick introduction to spreadsheets. I have a spreadsheet here. This happens to be a Google Docs spreadsheet, and they're called Google Sheets. Now this is free to use. It actually runs in your browser. And there's another kind of spreadsheet that's also free that I sometimes use that runs on the desktop, and that's LibreCalc. And that's free to download. Well, as you can see, we have columns here. Columns have letters in them. And after you get up quite a ways, they double letters. Like over here, you can see AA, AB, AC. We have rows. Rows have numbers. So up here in the upper left-hand corner, it's going to be A1. Now these are cells where you have an intersection of a row and a column. That's a cell. And as you can see, it's highlighted. It's B3. You can also have a range of cells. I've selected a range here. And this is going to be B3 through B8. And as you can see, you can put formats on these cells. So you can have text in cells. You can actually merge cells. So this is actually acting like one cell here, even though it's really composed of 4 cells. And you can have text that wraps around, because if you don't turn on text wrapping, it'll just run off the edge of the cell. You can see you can change the background color for the cells. You can change the font size in the cells. You can change the font positions of the cells. You can have it left side, right side, top, and or bottom. You can change the color of the text. Here I got kind of a light gray. You can also set borders on cells. Here I have the upper edge of the border a dark black. Here has the bottom edge black, and here's another bottom edge black. And you can change the width on those borders. You can do entirely around a box. You can do entirely around a set of boxes with nothing internal. You can make the borders dashed. So here you can see we did a border around a big set of boxes. And I did that because they're all kind of related. Here you can see I merged a bunch of cells vertically, here and here. Now, what about the values inside a cell? The values can be text, they can be numbers, they can be a function or an equation. And on numbers, you can do formatting, like you can move the spot for the decimal place left and right. You can have it be percentages, dollars, dates, or you can let the spreadsheet try to figure it out based on what the format of the text that you entered in. All right, now let's start talking about some of the inputs here. So this is just a number. I did not specify that it's a number. The spreadsheet software went and looked at this text and said, oh, this looks like a number, and just made it into a number. Now I did change the left and right position of the decimal point. So I can like move it this direction, fewer digits, or I can use it this direction, more digits. Now let's start talking about equations. So here's a really simple one. You can see up here in this area, the equation. And the equation always starts with, or function is actually a better word, function always starts with an equal. And then it's going to have cells and arithmetic operators. So in this case, we're taking cell D3 plus cell D16 plus D19 and D22. And we're just calculating the wing span. Now those spans come down here from inputs. So right here is a span. There's D13. Here's another span, D16. Another span, D19. And a tip span, D22. And that was this equation right here. So in general, that's how you do functions. Now they can get more complicated. You can have multiplication, you can have division, you can have subtraction, and you can have other functions that get called, like trigonometric functions. Here's an example of having a constant multiplied by a cell. Here's an example of using parentheses to make sure that this addition happens before the subtraction, because precedence matters. I'm not going to get a precedence, that's a pretty long subject, but in order to make sure things happen in the correct order, you can use parentheses. There's a division. Another thing Google Sheets can do is you can double click and you can actually bring up the same thing down here close, so you don't have to go all the way up here. So that's sometimes convenient. Now here's an example of a trigonometric function. There's a sign, and then the argument is inside the parentheses. And again, if you forget to put the equal sign in here, the spreadsheet's going to just think this is text. It's not going to realize it's supposed to be a function. Here's an example of how to do a power. So let's say you want to raise something to the power of 2. You'd use power, and then the input, and then 2. If you want to do square root, you put in 0.5 here. And again, this is another use of parentheses to make sure that the various operators happen in the correct order. Next, let's talk about how to enter a cell into an equation. Now you could just type it in, but you can actually do a little bit better than that. So let's say we're going to enter an equation here. I'm going to say equals, and now I can actually click on a cell and it'll enter it in there. And then I could do something like plus. And then I could click on another cell. And then when I'm done, I hit return. That's way easier than typing cell names in. Now let's talk about another thing that the sheet will do. Let's say I want to have the same exact equation on the next row down, this row down here. And I want to add the same columns together. I want to add this column and this column, just like we did up here for this row. What I can do then is I can select this equation, Control C to copy it to the clipboard. I come down and Control V to paste it. Okay, so we have D7 and J7. So this is row 7. Now look at this one down here. The spreadsheet knew that I was moving it down, and so it changed to row 8 automatically. So that saves a whole lot of time entering equations when you want to do the same equation over and over. You just want to change the row. Now it doesn't have to be just on the same row. Let's get rid of these two. Let's enter cell D7, and then let's add over here on the next row down on row 8. And let's hit return. So D7, J8. Now let's copy this one and let's paste it. So now you can see it did the same orientation relative to our original cell. So now we've got D8 and J9. So it moved everything down one row when we pasted it down one row. And of course, if we moved it to the right one row and did a paste, it would try to do the same thing, but that's not going to work very well. Let's go ahead and do it. Now it's going to come up with 0 because it's actually trying to use E7 and K8. So it moved everything relative to where I pasted it to. But that can be pretty convenient. Let's do a range of cells. Let's sum them together. So let's say I want to sum. Let's do sum. And I want to do this range. So I pressed and held, dragged, and then release. So you can see it did D7 to D9. So D7 to D9. And you can see for a range, there's a colon in between. Now, if you remember from part 2A, these 3 C's should add together to be 1, and they do. So that's great. Now, there's another thing we can do is we can actually keep cell numbers from changing when we do the paste. So let's go ahead and go back in here, and let's say we want to add, again, D7 plus J7. But we don't want D7 to change. So what we're going to do is go put a $D, $7. Now when I paste, like this, and let's bring it up. So you saw this $D, $7 did not change, although it did change the next row down, J8. So when you put a dollar in front of something, it won't change. Now you can do it only by row or only by column. Now here I did both the row and the column. That makes it much easier to enter equations, particularly down here, where I've got row after row after row where we're doing the same calculation all the way across. I can come over here, select an entire row, copy that, and then let's say I didn't have any of these others down here. I could then select a row and do a paste. If you just do a straight paste, it overwrites everything. Now you can do something a little different here in Google Sheets is you can do a right click and you do a paste special. So you can paste only values. So that would be the results of equations. You can do only the format, so the equations would not get copied. Or you can do the formula only. So formatting would not get copied, just the formulas. So that's, for the moment, enough of an introduction. Now let me talk a little bit about how I like to set up some of these spreadsheets that I'm using. Well, first I try to have the title be fairly meaningful. Here it says UWS-4 wingspan-wise lift distribution. Now at the moment this is only doing additional lift. We haven't added in basic lift yet. So I might make another sheet to do basic lift, or I might go ahead and add it in here into this so it does both additional and basic. I haven't figured that part out yet. I like to join a few cells up here to make a lot of space so I can put a paragraph in here talking about what the sheet is doing. And then sometimes I'll have an additional paragraph. In this case, I'm talking about which NACA technical report number I'm using as a basis for the equations that are being used in here. So that if I look at an equation and go, man, I don't remember what in the world this is supposed to be representing, I can go back and look at the technical report and figure that out. I use formatting, basically the colors of text and the cells, to figure out what's going on. I use a black background with white text for major headings on the columns. I use a gray background for headings, kind of minor headings. Now I use blue for cells where I enter data. Sometimes in the future I can come back and look at this and go, oh man, I don't remember which things are calculations and which are things that where I enter a data that's not a calculation. So I use blue to indicate cells where I'm entering numbers. I use green to indicate calculations where I don't enter the numbers. All these calculations are based on inputs, the blue cells. I also usually put a legend in here. So a dark blue, or actually I should say kind of medium blue, indicates a number that doesn't come from anywhere else. I'm just entering this here without any other basic information. A lighter blue means it's something that's probably calculated somewhere else, not within this sheet. Maybe I've done it by hand, maybe it comes from some other spreadsheet, and I entered it here manually. In general, these dark green ones, well, actually medium green, then light green. The medium greens are a result, and a light green are an intermediate calculation. I've used this legend often enough now that I remember what it means. This is basically here for someone else that's going to come and look at this in the future. And it's just off to the side where it won't cause any problems. Let's do a quick review of what we talked about in part 2A. This gamma of y is span along the wing, some span position. Gamma is a lift. That's composed of two parts. There's additional part and the basic part. Now additional part is multiplied by an angle of attack and the lift slope of the airfoil, or actually the lift slope of the wing, not the airfoil. So what we're going to be doing, calculating initially, is this gamma sub A, the additional lift, and then when we want to figure out the lift of the wing, we multiply by angle of attack and lift slope. So right now in this spreadsheet, we're really only interested in this part of the equation we just looked at. Now that gamma sub A is composed of three parts, if you remember correctly. C1 multiplied by a local chord divided by average chord at some position along the span. And we're interested, at least at this moment, in a span from 0 at the root to 1.0 at the tip. And then we got C sub 2, another constant, multiplied by the elliptical distribution. And then C sub 3 multiplied by some sweep correction factor. So that's what this spreadsheet is going to be doing initially. And then we multiply by the angle of attack and the lift slope. So let's go back and now look at our spreadsheet. So we're back at our additional lift spreadsheet. And you can see the first thing that I've got in here right now is C1, C2, and C3 that we just looked at. Now you can see it's light blue, which means I actually grabbed these from somewhere else. And in this case, I went and got these from a different spreadsheet. Let's not bother looking at that right now. I don't think it's really that important. Basically, it's just interpolation of some tables. And J down here is also interpolation of some tables. You may remember that from part 2B. Now here is where I put in the configuration of the wing plan form. Now I have this wing divided up into 4 sections. There's an inner flap section. Now this is actually the center section. The outer flap section, that's just outboard of the center section, but before we get to the ailerons. And then we have the aileron section, and then we have a tip section. Now on all these, we have the span of that section, so it's from the root out to the outer edge of the section. We have the sweep at the 1/4 chord line, and that's going to be in degrees input here. This is going to be the chord at the tip. The chord of the root is up here by itself, so chord of the tip. Section 2, basically the same information. So the span of that section, the outer flap section, the sweep at the quarter chord, and the sweep at the tip of that section. And same thing on section 3, aileron, and same thing on section 4, the tip section. Now these are all numbers that I entered. They were not calculated anywhere else. Now the lift slope for the wing, that's calculated somewhere else. I entered that here. I used a spreadsheet to do that. And then I also have the angle of attack that I'm interested in. And that's in degrees, and I can change that here, which will change the lift, and we'll see that shortly. Now I have a whole bunch of calculations over here to give me more information about the wing. And it's based on all of these configuration parameters over here. One thing it does is to let me do a sanity check, because I also have a lot of these calculations in another spreadsheet doing some just basic configuration calculations. So for example, I calculate the semi-span, so all the spans of those 4 sections together added up, and then I just do the wingspan, that's just multiplied by 2. I have a calculation that tells me what the quarter chord at the root is, and then I also then go through, and for each of these sections over here, I do some calculations like what's the surface area, what's the taper ratio of that section, what's the X position of the quarter chord, what's the mean aerodynamic chord, and where's the Y position at that mean aerodynamic chord. I do that for all 4 sections. And then down here at the bottom, I do some overall wing calculations. What's the total surface of the area? So we're just adding up these various section surfaces. What's the whole aspect ratio of the wing? What's the mean geometric chord of the wing? What's the mean aerodynamic chord of the wing? Where's the Y position of that mean aerodynamic chord? What's the sweep of the wing? Let's go back and talk about the mean aerodynamic chord just a moment. You may remember this slide from part 2B, and this is an equation for calculating the mean aerodynamic chord for a wing with multiple taper segments. So you take the surface area of one segment multiplied by the Y position of the mean aerodynamic chord, and you do that for each of the segments, and then you also sum up all the areas. So that's essentially what we're doing here. So let's bring that up. So J12 multiplied by J8. So that should be a surface area multiplied by a Y position of the MAC. Surface area, that's J8 multiplied by the Y position. That's J12. So that's the first section. Those two multiplied together. Here's the second section. Here's the third section. And here is the tip. And then down here, this is the surface area, J28. Remember, that is that area, 116, and divide by 2, because we're only interested in the semi-span, not the whole wing. Now, all these calculations up in here, at least up to this point, are either in degrees or length units of feet. Now, frequently for span in our equations, we're using 0 to 1, 0 meaning the root, 1 meaning the tip. So I converted this number to a 0 to 1 number just by dividing by the wing span, or actually a semi-span right here, 13 feet. And so that gives me a number of 0.45. So 45% along the span is where that Y position on the mean aerodynamic chord is. Now I also calculated the center of pressure from 0 to 1. Now you may remember that equation from part 2B. So that's this equation here, where this is actually for just a straight taper. We're going to replace this with our mean dynamic chord. This is the center of pressure for an elliptical wing, and this is a J that is a correction factor for sweep. And that C1, C2, and C3 are the same C1 and C2 and C3s that we have for the lift distribution. So in our spreadsheet, so this very first part here, D7 is our C1. K32 is our mean aerodynamic chord Y position. D8 is our C sub 2. And that's 4 divided by 3 pi. That is the elliptical chord center of pressure. And D9 is C3. And C10 is our J. So that's this number right here. And maybe we'll talk about J a little bit later. So that's everything we can calculate very easily just using the geometric parameters of the wing. So now let's start working on that gamma sub A, that additional lift. So one of the things I want to get is this Y star. That's Y positions along the span going from 0 down to 1. And I have to figure out some of those positions along that span I want to do calculations. Now I've already talked about the various sections of the wing. We have a center section. We have a mid section, which is also the outer flap section. We have the aileron section and a tip section. So that's these same sections that we talked about here and over here. So I decided how many points I want to divide each of these sections into. I just kind of arbitrarily picked 5 in the center section, 8 in the mid section, 8 in the aileron section, and then 3 on the tip section. And then I just do some simple calculations. I just divide up that span of the center section, and I can just use a little equation and evenly divide up that section into segments. No big deal. I did that for each of the sections. So now I have positions along that wingspan in feet. I also calculated the wing chord at those same Y positions along the wing, and that's just using some simple trapezoid calculations. No big deal. And then in order to get the Y star, I take that foot section divided by the entire semi-span, and that gives me a Y star. Now I also added another little calculation here that tells me how wide each of these sections is. So the distance halfway to the previous point and halfway to the next point, that's the span of that segment. That gives me a delta Y. Well, now we're going to get into the guts of calculating that lift distribution, the additional lift distribution. And that's taking local chord divided by average chord, the elliptical chord, and that F correction factor that you may remember from part 2A. Now these have not been multiplied by that C1, C2, and C3 coefficients yet. That actually happens over here. So here's an example of the local C divided by the average C. So the local chord, that's D40, divided by the average chord, which is the J30. Let's go take a quick look at that. Here's J, and there's 30. So the mean geometric chord. And the elliptical, that should just be an elliptical equation. So 4 divided by pi, and that is the square root of 1 minus the square of E40. E40 should be a Y position. There's E, yeah, that's Y star. So that should look like our eclipse equation. Right there, 4 divided by pi, square root of 1 minus y squared. Yep, so that's the equation there. And this F is something that I copied from another sheet. That's why it's this light blue color. Remember, the greens are calculations, but anything that's blue, particularly light blue, I copied from another sheet. All right, now let's look at these 3 columns. This is now multiplied by our various coefficients, multiplied by C1, C2, and C3. So for example, C1 of C over C average, remember that is this equation here. So that equation says $D $7, so that should be C1. Let's come back over here. $D $7, that's C1, yes. And that should be multiplied by C over C bar, which is this column here. So that is G39, and sure enough, that's G39. So we did that for all the Y's. And we did the same thing for here, C2 times the elliptical. So C2 is $D $8. Let's go take a look at that. D8, yes. So D8 and then multiply by H39. H39 is here. C3, $D $9, that's C3 cell, and then multiplied by F of Y. All right, so we now have the 3 portions of our equation. So all we need to do is add them together, and that's what this is here. So you can see this is dark green. That's telling me this is a result. It's not an intermediate, it's an actual result. So this is our gamma sub A, our additional lift distribution. So now we can calculate the lift for each segment. That'll be this column here. So we take our gamma sub A over here. That's going to be our local gamma sub A. And then we multiply by our y delta, this F over here. That's just the span of our segment along the wing. So that gives us lift. We sum all those up, come down here, and this gives us our lift before we take into account the lift slope and we take into account the angle of attack. Now I also added the shrink in here to use as a comparison. So you would compare shrink here with our gamma sub A. Now one of the things we're going to need to figure out what the maximum lift of our wing is we're going to have to figure out what the maximum lift coefficient is at each segment. So not the wing's coefficient of lift and not the airfoil's coefficient of lift, but the coefficient of lift at each segment. So that's what I've done here. So we take our M39, gamma sub A, and then divide by G39. And G39 is that C divided by C bar. So it actually backs out that part of our gamma, and that gives us our local lift coefficient. And now we kind of come to the culmination of what we're looking for. Now I call this gamma sub Y. It's gamma but without the basic part. So it's gamma sub A multiplied by the lift slope and the angle of attack. So we take our gamma sub A multiplied by D26 and D27. So if we come over here, D27 is angle of attack and D26 is our lift slope. Well, now that we have our gamma that includes lift slope and angle of attack, we can do the same thing for lift that we did over here. So we do basically the same thing. Take the gamma Y and again multiply by our delta Y. And again, that gives us our lift, and we sum it all up, and that gives us the total lift on the wing. So we can do the same thing by taking the lift that we calculated over here, this one, and multiply it by lift slope and angle of attack. The reason I want to do this one is when this one reaches the maximum coefficient of lift for the airfoil, we know the wing has started to stall. Now here is the maximum coefficient of lift for the airfoil itself. So you can see we're just barely underneath that right now. Let's go ahead and increase the angle of attack just a little bit. Actually, just go up a little bit. Let's go up by 700ths. Let's see what that gives us. I have it so that when the local coefficient of lift goes over the maximum, you can see it just barely did. 0.1692, 0.1691. So these two are just barely over that max. So the wing has just started to stall. Now, one of the things I wanted to do is figure out how close does this coefficient of lift of the wing, that's this number down here, this is the maximum coefficient of lift of the wing. We just started stalling. So I want to know how that compares to taking the maximum coefficient of lift of the airfoil, this number here, multiplying by 0.9, like you see in a lot of books. And the result I'm getting is actually 0.95. So this particular wing, this is the multi-tapered wing with tip, is getting a better maximum coefficient lift of the wing than the 0.9. We're getting almost 0.95. So that's actually pretty good, assuming that all this is right. So that is essentially what I wanted to talk about in this video. I know it was kind of quick, but we could end up spending a massive amount of time if I talked about everything in detail. I think that most of you that would actually be interested in trying to do this can probably figure out stuff that I left out. I think you'll be able to figure that out without any problem. You can always Google stuff. There's a tremendous amount of help information on Google's for the built-in functions that you can put in equations. For example, that conditional background color where it turned red when I hit the maximum coefficient of lift. You can look that up. It's easy to do. It's just a little bit different than the other formatting, which is kind of annoying. So one thing I did leave out in this video is doing interpolation. I left that out because I think trying to describe that is very difficult. I have a hard time remembering how to do it. The functions that you would use aren't the same for all the spreadsheets, so it'd be good for Google Sheets here, but I don't know if it'd be good for Excel. Almost certain it wouldn't be, and I don't know about LibreCalc either. I may do another video here in the future where I talk about interpolation on all three of those, on Excel, LibreCalc, and Google Sheets, and show how to do that. Well guys, that's really all I intended for this video. Part 2D will get into basic distribution of lift. And again, that includes how lift is changed when you deflect flaps, deflect ailerons, and add twist to the wing, washout. Anyway, thanks for watching. Until next time.